Why is this important? What is x minus x hat? That's the error in what domain? In the time domain, in the space domain, in the original signal domain. Okay? What is y minus y hat? That's the error in what domain? In the transform domain. Okay? And what we just showed is that the error in the transform domain is exactly the same as the error in the time domain. Okay? So our goal is typically trying to minimize this, right? So what we should do is we should minimize the error in the transform domain. So we should treat all the transform coefficients that we feed through the Q and the quantum entropy coder exactly the same way, right? We would like to minimize the loss on the transform coefficients. And also give you another idea, okay? In the transform domain, okay, if you throw away the small one, if you throw away the small transform coefficient, is the error large or small? Should you throw away the small guys or the large guys? In the transform domain, should I throw away the large coefficient or the small coefficient? The small coefficient, right? Because we make the least error when we throw away the small guys. So that's the key, right? How do we keep the large guys, throw away the small guys? Or when I make error, I should make small errors. I should make large errors in the transform domain. Okay? And that's why we love zero so much. Okay? Because if I have zero, I don't make any error. Right? If I have zero coefficients, I don't make any error. Is that true? Right? If I have zero coefficients, then I don't make any error. That's very important. And that's what we are trying to do when we, in other words, when we design transform, we have to take into account, okay, we have to design a transform such that it will be able to capture most of the energy using a few coefficients only. And the rest should be zero or close to zero. That is the way to go. Okay? So we should concentrate on the quantization of the transform coefficients. And next, let's talk about 2D. Okay? Because so far, with this, okay, with all this, we can only do 1D. We can only do transform in 1 dimension. Right? So how do we do transform in 2 dimension? Any suggestion? How do we do transform in 2 dimension? We should do all the rows and then all the columns. Okay? Or all the column and then all the rows. But the order doesn't really matter that much. Okay? So in 2D, this is what happens. Okay? X is n by n, and y is also n by n. So this is an n by n block of input signals. So for example, 8 by 8. Okay? Y is another 8 by 8 block of transform coefficients. T is the 8 by 8 transform matrix. Okay? So when you do it this way, what it means is that I'm transforming the columns. I'm transforming all the columns of X. And then I'm transforming all the rows of X. Okay? So if it's 8 by 8, I have to do the 16 time, right? Transform all 8 columns, and then 8 columns, and then transform 8 rows. Okay, separately. Okay? And in the synthesis, if I do this, I'm fine, right? In the synthesis, let's try to verify, right? In the synthesis, I need X is equal to Ts times Y times Ts transpose, okay? And substitute Y in here, I have Ts times Ta times X times Ta transpose times Ts transpose. These are inverse pair, right? Ts is the inverse of Ta, so it's an identity, cancel. This is also the inverse pair transpose. So identity transposes itself, so I get my X back. So everything is all fine. Okay? And if I pick Ts and Ta right, all I need is Ts is the inverse of Ta. If I have Ta transpose here, that's even better. That's the orthogonal case. Okay? So that's what happens in 2D. And in 2D orthogonal, you put the transpose here. This is identity. This is another identity. You get your signal back. The nice things about orthogonal is that you don't have to worry about designing the synthesis, okay? It's automatically given to you. And it also has this norm preservation properties, okay? If you have TS instead of TA transpose here, okay, you cannot have really norm preservation. So when you don't have orthogonality, you have to make sure you're close. You're close to it. Okay? If you're too far away, you lose this norm preservation property. And it can be, then you have to be really careful. So, an example of this would be the DFT that I'm just trying to repeat a lot of the things that Min said before. So for n equal to 4, it turns out that the matrix look like this. And you can easily come into MATLAB, type these things in, verify that it's actually orthonormal. Okay, actually no, it's orthogonal because I'm not scaling the one up here. Okay, now so this is the DFT, and the next question that you should ask is that fine. There are so many ways that you can choose the transform. So what transform is the best in terms of compression and generate the largest amount of zero copies, right? Generate the largest amount of zero copies. So let's pose this question this way. Okay? Let's investigate this problem. Design the optimal linear transform. Okay? Or in other words, amongst all the linear transform, among all the matrices that you can pick, which one should you choose? Which one is the best decorrelation, offering the best compression? Okay? So the problem is this. So this is a formal problem statement. Okay? Start with an endpoint signal X. Okay? Y stands stationary and all that. Okay, zero mean, Y stands stationary, random process. That's the only way we know how to model our signals. Okay, given that endpoint signal X, find the set of orthonormal basis function phi such that the mean square error between the L point truncated representation. That means you throw away. You only keep L coefficient. You throw away the rest. Okay, see. So I only keep maybe the first L, okay? The order is not that important. I don't mean that you all should always keep the one up front, but you can always permute it so that the guys who keep are up front, right? So let's say you permute and only keep the guys up front, throw away the rest, okay? How do I pick phi such that the difference between this guy and the original signal in the mean square sense is minimum? Okay? So that's the problem statement. How do we solve this? Same idea as we have been doing before. We're going to try to write mean square error between x and x hat, and we're going to try to do some derivatives, right? And hopefully we're going to come up with the phase. Okay, so that's the overall game plan. So let's remind you that the orthonormal constraint means this. The dot product between phi I and phi j is just delta I minus j, orthonormal, okay? And then I also remind you that the autocorrelation matrix of the signal is defined as this, which is just the expectation of the outer product of x and x transpose. Okay, so this guy is just the expectations of x times x transpose, where x is a column vector. Okay, x is a column vector. So, how do we start? First, MSE. Okay, MSE is the expectations of x minus x hat, L2 norm squared. Agree? Okay, and then we try. What is x? X is a linear combination of the phi. Okay? X is a linear combination of the phi. So I could write x is yi phi, and here I go from 0 to n minus 1. Means that I have everything. I keep every coefficient. Okay? But x hat is the truncation, right? That means you throw away. You only keep the first L guy. And L obviously is much smaller than n. Okay? You only keep a few coefficients. Okay? So x hat is just a summation I from 0 to L minus 1 yi phi squared. Okay? Now, so whatever they share, okay, give me 0. Okay? But whatever I throw away is this. These are the guys that I throw away, right? These are the errors. See? I throw away the guys from L to n minus 1. These are the guys that I throw away. I should minimize this expectation. Minimize this expectation, right? So this is the next step. So instead of writing it as L2 norm, I will convert it to inner product. Okay? Convert it to inner product, and I can write this as the expectation of these two inner product of these two guys. This dot product with itself. Okay? And then so this is the same as doing expectations of summation of these guys times the summation of these guys. Okay? There's no problem. It's just standard manipulations of matrix and vectors. Okay? So next, I'm going to be able to, okay, since the phi I dot product of phi j give me delta I minus j, what I pick up is only the guys in the diagonal. Right? Because if you're off diagonal, you automatically get eliminated. Okay, so I only pick up the guy in the diagonal, which means that it's only the yi. Okay, so this is exactly what we expect. Okay, the error, the mean square error, is simply the the energy of all the coefficients that you throw away. Right? We just show that the energy in the error in x is the same as the error in y. And in y, we're throwing these guys away, so that's the error that we make. So